Question number 16 says, a 2.004 gram sample of calcium is completely reacted with oxygen to produce 2.804 grams of calcium oxide. What is the mass percentage of oxygen in calcium oxide? Well, we have the mass of our calcium oxide, which is 2.804, and we're starting out with this much calcium, 2.004 grams. So that means that the remainder of the mass, okay, anything that doesn't take up that 2.004 grams is going to be oxygen. And so we can calculate the mass. The mass of oxygen is going to be equal to 2.804 grams, subtract 2.004 grams, and what's left over is going to be 0.800 grams of oxygen. So now we have our mass of oxygen, and if we wanted to determine the mass percent of oxygen, we're going to take the mass of oxygen, right? That's the mass of oxygen in the calcium oxide. We're going to divide that by 2.804 grams. So that's the mass of the total mass of the calcium oxide, and then we're going to multiply that by 100%, and we end up with 28.5% right there. So 28.5% oxygen. Question 17, how many grams of iron are in 16.55 grams of the mineral siderite? And we have the formula here, FeCO3, so its name would actually be iron 2 carbonate. Anyhow, so that's a common name, siderite. Anyhow, there's a couple of ways that you could solve this problem, but I think one of the easiest ways is to look at the molar ratio of the number of moles of iron in 1 mole of siderite, right? For every 1 mole of FeCO3, we have 1 mole of iron, 1 mole of Fe. And so if we use dimensional analysis, we can say we have 16.55 grams of iron 2 carbonate or siderite. And we know that in 1 mole of FeCO3, we have 115.84 grams of siderite, FeCO3, fix that. And where did I get this mass from? That's the formula mass, and I calculated that using the periodic table. I added up the mass of 1 iron, 1 carbon, and 3 oxygen atoms. So I've got that. And then I know that in 1 mole of FeCO3, I've got 1 mole of iron. Okay. And then I also know the mass of iron in 1 mole, and I get that from the periodic table. I know that in 1 mole of iron, I have 55.85 grams of iron. And look, all of our units are going to cancel out. Our grams of siderite, our moles are going to cancel out, our moles of iron cancel out, and we're left over with the number of grams of iron. And when you punch all that into your calculator, you end up with 7.979 grams of iron. Let's try question 18. Which of the following is silicon disulfide? This is going to be a covalent compound because it's made out of a nonmetal, sulfur, and a metalloid. Silicon, there are no metals in this compound, so it's definitely not ionic. And so we have no prefix in front of our silicon, so that indicates that we have 1 silicon, and then we have the prefix di in front of sulfide, and so that indicates that we have 2 sulfurs like that, and so here is our answer, SiS2, silicon disulfide. Question 19, what is the name of P2O5? Well, again, this is a covalent compound because it is comprised completely of nonmetals. Phosphorus is a nonmetal and oxygen is a nonmetal. And so we have to use prefixes. For our phosphorus, we're just going to name it as phosphorus. And since there are 2 of them, we're going to say it's diphosphorus. And then we have 5 oxygens. The oxygen suffix changes to "ide", and so we have oxide, and we have 5 of those, and so it's going to be pentoxide. It might be a knee-jerk reaction to say it's pentaoxide, but there's a little rule that when the second element begins with a vowel, we drop the A from the penta, so it just becomes diphosphorus pentoxide. Number 20, which location in the following chemical symbol is the correct location for the mass number of an isotope? Well, the correct location for the mass number is right here, okay? on the top left. So it's going to be E. This is where we have the mass number, which is the sum of protons and neutrons. Down here, D, this is where we have the atomic number. B, that's where we would put a charge if we had an ion. And C, well, that would be where you would put a subscript if you had more than one of the same element in a formula. So the answer is E. That is where we find mass number. Number 21, determine the number of moles in 27 grams of dinitrogen pentoxide. Well, if we're going to convert grams into moles, we're going to need the molar mass of dinitrogen pentoxide. And so for that, we're going to need its formula. Well, dinitrogen pentoxide is made completely from nonmetals. We have 2 nitrogens and we have 5 oxygens. Then I'll go over to the periodic table and I'll tally up the mass of 2 nitrogens and 5 oxygens, and I get a molar mass of 108.00 grams per mole for N2O5. And now I can set up my dimensional analysis. So I start with 27.00 grams of dinitrogen pentoxide, and I know that in 1 mole of dinitrogen pentoxide, I have 108 grams of dinitrogen pentoxide, like that. All right, and so we can cancel out the mass, or the grams of dinitrogen pentoxide. We're left over with the units of moles of dinitrogen pentoxide. And so when we put that in our calculator, we end up with an answer which is 0.2500 moles of N2O5. And we should have 4 significant figures because we were given 4 significant figures in our mass of dinitrogen pentoxide. And so here's our answer, 0.2500 moles. Number 22, what is the mass in grams of 3.011 times 10 to the 24 molecules of sulfur trioxide? Well, if we want to get the mass in grams of sulfur trioxide, we're going to have to find its molar mass at some point. So sulfur trioxide is a covalent compound. It consists of 2 nonmetals, sulfur and oxygen. So we have 1 sulfur and 3 oxygens. I've already gone ahead and tallied up the mass of that, and it is 80.07 grams per mole for sulfur trioxide. So let's start our dimensional analysis. We have 3.011 times 10 to the 24 molecules of SO3. And we know that in 1 mole of SO3, we have 6.022 times 10 to the 23rd molecules, okay, of sulfur trioxide. So we have Avogadro's number of molecules of sulfur trioxide in 1 mole. And you can see that molecules of sulfur trioxide will cancel out. Next, we want to use the molar mass as a conversion factor to enable us to calculate the mass of sulfur trioxide. And so we'll put that in 80.07 grams of SO3. That's the mass of 1 mole of sulfur trioxide. And so you can see that moles of sulfur trioxide cancel out. And I'm left with my answer, which is 400.3 grams of sulfur trioxide. And what do you know? That happens to be one of the answers. Question 23, calculate the mass percentage of carbon in chloroacetic acid. And so the mass percentage of carbon is going to equal the mass of carbon in divided by the total mass of chloro. I'll just write here CH2, Cl, COOH. So the total mass, and then we multiply that by 100%. Well, how many carbon atoms are in this molecule, chloroacetic acid? You can see that there's one here and there's another one here. Okay, so there's 2 carbon atoms. So when I tally up the mass of 2 carbon atoms, I'm going to put 2 times 12.01 grams per mole. And then I've gone ahead and I've already added up the entire mass of chloroacetic acid, which of course has 2 carbons, 1, 2, 3 hydrogens, 1 chlorine, and 2 oxygens. And when you add all that up, again, which I've already done, you get 94.496 grams per mole, like that. Okay, and then we're going to multiply all of that by 100%. Well, you can see that the molar mass of the 2 carbon atoms will cancel with the molar mass of the entire compound, our chloroacetic acid, and we multiply that by 100%, and we get that the mass percentage of carbon in this compound is 25.42%. And so you should be able to calculate mass percentage of any element in a compound. Question 24. A certain oxide of vanadium is 32.02% oxygen by mass. Determine the empirical formula. Well, we know the compound is made out of vanadium and oxygen, and what we're trying to do is we're trying to figure out an empirical formula, so figure out the relationship between the number of moles of vanadium and the number of moles of oxygen in our compound. Now we're given that we have a certain oxide and it's 32.02% oxygen by mass, so what we should do is we're going to assume that we have a 100 gram sample of the entire compound. So that means we've got 32.02 grams of oxygen, and the mass of vanadium, so mass of vanadium is going to be equal to 100 grams subtract 32.02 grams. That's going to equal, what, 67.98 grams of vanadium. So now we figured out that we have 32.02 grams of oxygen in our compound and 67.98 grams of vanadium. And so the next step will be to simply determine how many moles of oxygen do we have and how many moles of vanadium do we have, because the subscripts represent molar ratios, and so we're going to divide the 32.02 by the molar mass of oxygen, which is 16.00 grams per mole. Okay, you can see that grams are going to cancel out, and I end up with 2, so I end up with a number of 2 moles. And then for my vanadium, I'm going to do the exact same thing. The molar mass of vanadium is 50.94 grams per mole. And when I do that, mass cancels out, and I end up with 1.33 moles. So if I was to put that in my formula, I'd end up with something like vanadium 1.33, oxygen 2, okay? But we're not going to have a fraction. If you were to take this formula here, V 1.33, oxygen 2, and if you were to multiply that by 3, you'd end up with vanadium 4 and O6. But still, that's not an empirical formula, right? That's not the simplest whole number ratio of vanadium and oxygen in this compound. If we divided the whole thing by 2, we'd end up with V2O3, and we can't simplify that any further. And so the answer is going to be, the empirical formula is V2O3. Question 25, according to the following chemical equation, how many moles of KO are necessary to completely react with 13.9 grams of H2O? And we have a balanced equation, right? We have a balanced equation right here. Okay, and we're starting it with 13.9 grams of water. And we want to figure out how many moles of KO are necessary to completely react with this much water. Well, remember, the stoichiometric coefficients 4, 2, 4, and 1, those represent the relative number of moles of each compound in this reaction. So that means that when I consume 2 moles of water, I'm actually going to consume 4 moles of KO. So the first thing we need to do then is determine the number of moles of water that's being used up. So how many moles of water are there in 13.9 grams? Well, we can use the molar mass of water to determine that. So we'll put 1 mole of water, and I've gone ahead and calculated the molar mass of water, which is 18.01 grams of water. And you can see that the mass of water cancels out, and we'd be left over with moles of water, but we want the moles of KO. And so we're going to have to use another conversion factor, and we're going to go to our balanced equation to get that conversion factor. And it's right here that when we consume 2 moles of H2O, we end up consuming 4 moles of KO, like that. Now you can see that moles of water cancel out, and we're left over with the units of interest. And so we end up with 1.54 moles of KO, like that. And it just happens to be an answer right here.